Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, what we're going to be doing is showing a theorem that is going to tell us what is the distribution of the sample variance if we have a sample of observations that are normally distributed. Okay? This is the theorem that we're going to be showing in this video. Okay, so as advertised, right, we have a random sample of size n, and we have that these observations, these random variables, have a normal distribution with mean mu and variance sigma squared. Okay, now S square represents the sample variance, meaning the sum of yi minus y bar squared divided by n minus 1. Okay? So what we want to show is, what we are going to show is that n minus 1 times S squared divided by sigma squared, okay, has a chi-square distribution with n minus 1 degrees of freedom. It also turns out that y bar and S squared, the sample mean and the sample variance, are independent. Okay? We are not prepared to prove the independence of y bar and S squared. Okay? You will be showing that maybe in sta258 or for sure in sta437. Okay, so the part that we're going to be showing is this, that the distribution of n minus 1 times S squared divided by sigma squared, okay, n minus 1 times the sample variance divided by sigma squared, is going to be a chi-square with n minus 1 degrees of freedom. Okay, here we go. Proof. So, first, let W, right, be the following quantity. Okay, we are going to introduce this quantity. The sum of I going from 1 up to n of yi minus its mean mu divided by sigma. Can you see that basically what we're doing there is standardizing the yi's, right? Because we know that the yi's have a normal distribution with mean mu and variance sigma squared. So these guys are standard normals. Okay. So, in another video, we have already shown that if you have a standard normal and you square it, you end up with a chi-square with 1 degree of freedom. Okay? And we have also shown that the sum of n chi-square distributions with 1 degree of freedom is going to have a chi-square distribution with n degrees of freedom. Okay, so W is going to have that distribution, right? A chi-square with n degrees of freedom. Okay, we can easily show that. We have actually already shown that using MGFs. Okay, now we're going to do a kind of a trick. Note that the quantity that we are interested in is not yi minus mu divided by sigma the whole thing squared. No, it's something similar. Instead of subtracting the population mean mu, we're subtracting the sample mean, okay, y bar. So we would like to introduce that there. So in order to introduce that y bar that we need, we are going to be doing something that is very popularly done in math, right? We are going to be adding a 0. We need a y bar. Well, add and subtract that guy. We're adding a 0, and now that guy appears. Okay? No problem, right? It's just a 0. We haven't done anything illegal. Now, let me do a little bit of algebra here. So this would be the same as, let me factor out that sigma. This is the same as 1 over sigma squared. Let me get rid of this, right? We don't need it anymore. Let me expand it. What we're going to have here is yi minus y bar squared plus y bar minus mu squared plus 2 times the cross product. Okay? This times this. Agreed? Again, we're just expanding this, right? We're just doing a little bit of algebra. So square of that fraction, right, is just numerator squared, which is this, divided by the denominator squared, which is 1 over sigma squared, and we factored out that guy. Okay, so now that would be the same as this. Let me copy paste this guy here. Yeah. So that's the same, right, as this divided by sigma squared plus, now we have that, and it would be note that we have the sum of y bar minus mu squared, right? I goes from 1 to n, so what we have is n times y bar minus mu squared divided by sigma squared. Okay, so let me write that down. We have this guy here, and we have, right, y bar minus mu is a common factor, right, and then we're going to have 2 times y bar minus mu times summation of yi minus y bar, the whole thing divided by sigma squared. Okay, so let me copy this here, and let me place that guy there. Now what I need is a summation. I goes from 1 to n of that guy, and then we are dividing this by sigma squared, right? That's a common factor. Okay, agreed? No problem, right? Okay, so now I want you to note something about the third term in that sum, right? So note that this guy here, summation of yi minus y bar, is the same as this. This is just a summation of y i's, right? Oh, well. Summation of, yeah, y i's. I goes from 1 up to n, yi, no problem. And then we have summation of y bar. I goes from 1 up to n, so that's minus n times y bar. But if we recall how y bar is defined, well, y bar is just summation of yi's divided by n, right? So let me be very specific here. This is just going to be the same as this, divided by n, right? That's the definition of y bar. So these n's cancel out, right? And what we have is summation of yi minus summation of yi, which is just a beautiful 0. Okay, meaning that this guy disappears, so we are only left with these two terms. Okay, so W will be just the sum of those two terms. Let me copy paste those guys here. So W is just this. Make sense? Are we good? Okay. Now, let me rearrange these guys. yi minus y bar squared divided by sigma squared, that would be the same as this. I want to make it look nice, right? well, let me just point something out. Maybe there's no need for me to write that much. See? Summation of I goes from 1 up to n of yi minus y bar squared divided by sigma squared. That happens to be n minus 1 times s squared divided by sigma squared. Right? Can you see that? Right? This is the same as this. So let me write that down. That w is the same as n minus 1 s squared divided by sigma squared. N minus 1 s squared divided by sigma squared. Okay? Plus this guy here. Okay? Are we good thus far? Okay? Okay. And just a reminder, right? Where the sample variance s squared is defined as follows. S squared is just the summation of I goes from 1 up to n of yi minus y bar squared, and we are dividing that by n minus 1. Okay? That's the definition of sample variance of s squared. Okay? Okay. So now let me just call this guy, that equation we just found, let me call it hashtag. Okay? Just to keep it in mind. Okay? So now what I would like you to see is remember this, right? So if we let xi, let's call it xi, we're already using yi for something else. If we let xi be just the following quantity, yi minus mu divided by sigma, right? Clearly that quantity, right, given our assumptions, xi has a normal distribution with mean 0 and variance 1. So it is a standard normal, right? And I'm just reminding you what we observed at first, that w is the sum of n standard normals squared. Okay? So note that w is going to be the sum of those xi's squared, right? Okay, so we know that if you square a standard normal, you have a chi-square with 1 degree of freedom. So these guys are independent, so we have the sum of n independent chi-square these random variables with 1 degree of freedom. The distribution of W is going to be a chi-square with n degrees of freedom. Okay? Okay. Now, another observation. Oh, there. Another observation. See that quantity here? Y bar minus mu squared divided by sigma squared divided by n. Okay? So also note that y bar, right? So note that observation number 1, this. Observation number 2. Y bar. Let's pay attention to y bar. We have y1, y2 up to yn. They are normally distributed with mean mu and variance sigma squared. In another video, right, we have already shown a theorem that tells you the distribution of y bar. Remember what's the distribution of y bar, the sample mean, if you have a collection, a sample of n normally distributed random variables. Well, what we showed is that the distribution of y bar is going to be normal, again, with the same mean and variance sigma squared divided by n. Okay, so same mean, but the variance will be affected by the sample size. Make sense? Okay, and we have shown this before. Okay, so but now that implies that if we compute, if you're interested in the following quantity, y bar minus mu divided by sigma divided by the square root of n, that would be the standard deviation, right, of y bar. Well, then this quantity here, right, which by the way is equivalent to the following, let me rewrite this guy like this. Okay, let me do it here. Y bar, then I just need sigma, and this guy here multiplied by the square root of n. Okay, square root of n. You guys agree that this is equivalent? I just did a little bit of algebra. Okay, so the point is, clearly we just standardized y bar, so the distribution of that quantity is a normal 0, 1. Okay, so what that means, what that implies is if this guy is a normal 0, 1, if you square it, you end up with a chi-square with 1 degree of freedom, right? So let me write that down here. Let me square that guy. Oops, no, not what I wanted. If I square that guy, then the distribution is a chi-square with 1 degree of freedom. But a nicer way of writing down, oops, not what I want here. A nicer way of writing this down would be just like this. That's the same as just n, and then we have a square here, and then we have another square here. Okay, so n times y bar minus mu squared divided by sigma squared has a chi-square distribution with 1 degree of freedom. Agreed? But by our equation hashtag, right, this is the second term. Okay, so let's recap what we have done thus far. First, W, the one that we defined at first, that quantity is a sum of n standard normals squared. So clearly the distribution of W is going to be a chi-square with n degrees of freedom. That's what we have on the left hand side of our hashtag equation. This guy W has a chi-square distribution with n degrees of freedom. Now the second term that we have here, n times y bar minus mu squared divided by sigma squared, what we have shown here is that that guy has a chi-square distribution with 1 degree of freedom. Agreed? Okay. So, let me refer to this guy, right, as c squared. Is that okay? We will refer to this guy as c squared. Okay. So let's rewrite hashtag. Okay. Rewriting our equation hashtag, what we have is that W is the same as n minus 1 s squared divided by sigma squared plus a normal 0, 1 squared. Okay? Okay. Now, note that y bar and s squared are independent. As I said at the beginning, we are not prepared to show that, but we're going to be using it. Okay? So, let me just say that from the fact that y bar and s squared, the sample mean and the sample variance are independent, it follows that c squared, that guy is a function of y bar, right? And s squared are independent. Okay? Make sense? Okay? Okay. Now, let's use the definition of MGF for W. Okay? So by definition, the MGF of the random variable W is just the expected value of e to the power t w. Agreed? That's just the definition, right? We know that from sta258. Now this will be, in this case, the same as the expected value of e to the power t times this. Make sense? So e to the power t times this. Because that's what W stands for, right? Okay. So now let's do a little bit of algebra. So this is the same as t times the first term, t times the second term, right? No problem. Okay, but this is where things turn interesting, and that's why we need the independence. So first we just we're going to be doing a little bit of algebra. So this expression here could be is equivalent to just that product of exponentials. Make sense? Oh, looks ugly. It was better before, right? Okay, let me rewrite it. Okay. Make sense? So again, just doing a little bit of algebra here. This is the same as the product of these two exponentials, but now we're going to be using the independence. Since c squared and s squared are independent, right? The expected value of that product is the same as the product of expected values. Agreed? Okay, but now if you take a look at this, this would be by definition, right, the MGF of the variable n minus 1 s squared divided by sigma squared times the MGF of z squared, right? So what we have here is that the MGF of the random variable w is the same as the MGF of this random variable here times the MGF of that normal 0, 1 squared, at standard normal squared. Okay, just by definition. Now remember that we said that W has a chi-square distribution with n degrees of freedom. That was one of our observations, right? So now let's take a look at our table in our textbook, right? We have used that table before. That's page 838. Let's find the MGF of a chi-square distribution with n degrees of freedom. In this case they use a Greek letter, nu. So for n degrees of freedom we are going to have 1 minus 2 times t minus to the power minus n divided by 2, right? That would be the MGF of a chi-square with n degrees of freedom. 1 minus 2 times t to the power minus n divided by 2. Okay, so on the left hand side we have 1 minus 2 times t to the power minus n divided by 2. Then here we just have this guy, and the other one, the MGF of z square of a normal 0, 1, we know that z squared is a chi-square with 1 degree of freedom. So the MGF looks similar, but instead of n degrees of freedom we only have 1. So let's just change that accordingly, right? And then, you know, just a little bit of algebra. Okay, let's solve for the MGF of the quantity, the transformation of interest. So we want to solve for this guy. So it's going to be, right, this will be divided by that, which means that we're going to have, instead of a minus, we're going to have a plus, right? So we're going to have plus, oops, up there, right? In the exponent we're going to have plus 1/2, which is the same as this, right? Let's do a little bit of algebra here. This is going to be the same as minus n minus 1 divided by 2. Agreed? Those two expressions are equivalent. But now if you take a look at this expression here on the right hand side, that is the MGF of a chi-square distribution with n minus 1 degrees of freedom. So by the uniqueness property of MGFs, n minus 1 times s squared divided by sigma square has that distribution. Okay, so this is the MGF of a chi-square with n minus 1 degrees of freedom by the uniqueness property of MGFs. Our guy, n minus 1, the sample variance divided by sigma squared, has that distribution. And we're done. Okay? Okay, so let's summarize what we did here today. We showed that theorem, right? That if you have a sample of n random variables coming from a normal with some mean mu and some variance sigma squared, if you are interested in the following transformation, the following function of these random variables, n minus 1 times the sample variance divided by sigma squared, then the distribution of that quantity will be a chi-square with n minus 1 degrees of freedom. Okay? Okay. And now in the future, in the near future, what we're going to see is that we will be using that theorem, that result, to do inferences about sigma squared, okay, the variance. Okay, but we're going to be able to say something about the variance sigma squared from the sample variance. Okay, and that we can compute from our sample, from our observations. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.